Today, I'd like to talk about machine learning on non-curated data. So, how to do data science with dirty data in Python. Dirty data is one of the most pressing challenges of data science in the industry, as industry surveys show. One of the challenges is that machine learning works best after casting data to numerical arrays. However, in real life, we often work with tables such as this one, which are not made of numbers. They typically come as a pandas data frame. So there's a variety of challenges that we face. The first one is that we need to encode every column. For this, we'll use transformers to vectorize each column. And I'll discuss how we can use the column transform in scikit-learn to do this. Now, one of the problems is that some of the categorical columns do not expose clean categories, but rather many morphological variants. This is what I called dirty categories, and I'll discuss how this can be addressed with the dirty cat library. Finally, some of the columns may have missing values, and I'll discuss how we can use progress in statistical learning to tackle these missing values. So this talk will teach you how to vectorize and efficiently learn on dirty tables. Let's start with column transforming. I'll talk about how we can take pandas data frame in and output numpy arrays. So this is basically pre-processing. Often, we're given data as a pandas data frame, such as this CSV file, which contains record of employee salary. What we want to do is to convert all the values to numerical values. And for this, we'll transform each column. For instance, the gender column is a categorical column, and we'll use one-hot encoding to transform it to numerical columns. In scikit-learn, we'll do this with a one-hot encoder, and we can transform this column in a series of columns of zeros and one that encode the various possible values. For the column comprising dates, we can use pandas datetime support using pandas to datetime and then transform it to floats. So for all this, we'll be using transformers. For instance, the one-hot encoder. The one-hot encoder will first fit the column and then transform it. During the fit, it stores which categories are present. During the transform, it encodes the data accordingly. For machine learning, this is more appropriate than pandas getDummy function, because the columns are defined from the train set and do not change with the test set. So this is the idea of separating fitting from transforming. This is useful because it avoids data leakage, and it can be used in a pipeline or in cross-val's core. And pipelines are extremely useful thing that we should use as much as possible. For dates, we'll need to use the function transformer. So what we'll do is that we'll define a small function, date2num, that will use the pandas.toDatetime function and then cast to float. We'll make sure when we return the corresponding vector to reshape it so that it has a 2D output. And then we can wrap this function in the function transformer. This way, we get a transformer that can be applied in a pipeline. Now, we'll need to assemble these different transformers. So we'll need to apply all these different transformers to each column. For this, we'll use the column transformer, where we specify which transformer gets applied to which column. And then it can fit and transform a full data frame. So this allows us to go from data frame to array with heterogeneous preprocessing and feature engineering. Now, this is extremely useful because we can start using scikit-learn's model selection framework directly on data frames. And so we can pipeline this column transformer with, say, a gradient boosting classifier, and then use cross-val score. Now, I'd like to cover the encoding of dirty categories. This is the PhD work of Patricio Cerda. The idea being that I'm given such a column, such as the one that you have here, giving the employee position title, and in this column there's the notion of categories. There's the notion of police officers, of bus operators, but they have many variants. So we need to be able to learn on these variants. The typical solution would be to apply one-hot encoder. However, this type of column breaks the one-hot encoder. The challenges are that we have overlapping categories, the different variants of police officer. We typically have a very high cardinality. In this specific data set, we have 400 unique entries for 10,000 rows. And we have some very rare categories. There's only one architect 3 in the data. We might have new categories in the test set. So one-hot encoding isn't a very efficient approach. The typical point of view is to do data curation. So typically borrowing techniques from database normalization. So in machine learning, this is a feature engineering step. For instance, we might separate the position and the rank. So separating out police officer, social worker, and different ranks. Another point of view from database is that we need to recognize and merge different entities. So for this, we'll be using deduplication or record linkage techniques. The goal here is to output a clean database. So for instance, if we have various variants of a given company name, Pfizer, we can try to recognize these and merge them. However, this is very difficult to do without supervision, without examples of successive merge. And it's potentially suboptimal. For instance, if I have Pfizer Corporation Hong Kong and Pfizer Pharmaceutic Korea, should I merge them or not? That depends on the analytical question. These steps are very hard to make automatic and turnkey, and I claim that they're harder than supervised learning. So our goal is to do supervised learning directly on the non-clean data. So we want to do supervised learning on dirty category, and the idea is that the statistical question should inform the curation. So we should decide whether or not to merge the Hong Kong and the Korea branch depending on the analytical question. The first thing that we did a few years ago was that we tried to leverage the strings in this data with the idea that string similarities across the different entries carry a lot of information. So we adapted one-hot encoding. And so instead of having this 0-1 encoding, we put in an encoding that's based on the similarity of strings. One, if the string is similar to a given prototype, but a continuous string distance if it's not exactly equal but similar. So with this, we can link existing categories in the data, we can fit new categories, and we can predict to new categories, and we get a numerical encoding. So this idea is implemented in the Dirty Cat software, and it's called the similarity encoder. And as the previous transformers, it's a transformer, and it can fit and transform columns of a data frame, giving you numerical values instead of strings. Another approach that was done almost 20 years ago is called the target encoder. And the idea is that we're going to represent each category by the average target. For instance, if we're trying to predict the salary, we're going to represent police officer 3 by the average salary of police officer 3. So I've shown you here the column represented for the target encoder. So you can see that it is a one-dimensional representation, basically sorting out the different employee job titles as a function of their corresponding salary. We can see that the person who makes the least amount of money in this data is the crossing guard, and the people who make the most amount of money in this data are the managers. And there's something interesting here, is that there's no clear order in the manager. Manager 3 makes less money than manager 1, which makes money than manager 2. We need to be careful about this because there's going to be noise, there's going to be unexplained signal in the data. So this encoding isn't perfect. However, the idea is that by ordering the data like this, by embedding the data like this, we're creating a good representation for learning, so a representation on which it's going to be easier to learn the prediction function that we're interested in. So, embedding close-by categories with the same Y can help building a simple decision function. This is also included in the Dirty Cat software. It's called the target encoder, and it also has a fit transform or a fit transform method. So with Patricio, a few years ago, we did a thorough numerical evaluation on real data set of those different strategies. And what we showed is that first, accounting for strings really helps predicting in many real-life data sets that similarity encoding works best with what's known as the n-gram similarity, which is basically counting the number of substrings in common, that gradient boosted trees work very well on tabular data, and that's something that we've been seeing in many studies over the years. What we also saw was that target encoding was very beneficial for non-string data, where we cannot use similarity encoding, but for this, we need to use complex models, such as tree-based model. Target encoding does not work well when it is used as a preprocessor for a linear model, but it works very well for a complex tree-based model. Now, the problem is that in many real-life data sets, the number of categories keeps increasing as the data set gets larger. So we have a problem of blowing up the dimension. This is a bit similar to how new words appear in natural language. Now the problem is that we get a very high dimensional embedding of our data, a very high dimensional vectorization of our data. And this will give us statistical problems and computational problems. So we need to tackle this high cardinality. The techniques that we're using here are prototype methods, whether it is similarity encoding or one-hot encoding. They will compare a given category to a reference prototype. So the question is, how do we choose a small number of prototypes? We can take the complete training set, which is what we've been doing so far. This will lead to huge dimensionality. We can take the most frequent categories, but you can easily see how this might go wrong. Maybe the right prototypes are not in the training set. For instance, if my data is made of big cat, big dog, fat dog, you can see here that the right prototypes are probably big, cat, fat, and dog, which are not the original categories. So what we need to do is that we need to estimate the relevant prototypes. Here, we're going to be saved by the fact that n-grams, so length n substrings, grow as the number of rows grow, but they are pretty much repeated in the data. So there is redundancy, and there's redundancy in the substrings. The idea being that those new categories share substrings. And you can see it if you look at the actual raw categories. So for instance, if we look at the table of drug names, here we have many different drugs, but all of these have in common the fact that they're alcohol. If we look at their employee position title, we can see substrings that keep reappearing. Police, officer, technician, senior, 2, 3. So we'll need to be able to extract those substrings to learn from them, and we'll build a representation from those substrings. And I'll show you how a model can do this automatically. The idea is that we're going to try to find latent categories. So we're going to try to guess categories from the data. And for this, we're going to use topic modeling on substrings. So we're going to represent the string by all its substrings of a given length. So for instance, all the length 3 substrings, which we call the 3 grams. And then we're going to model the full string as a linear combination of substrings. So we're representing each category as a count of the substrings that it contains. So we get a matrix of those counts. And then we're going to do matrix decomposition, which is a common topic modeling technique, and represent this matrix in a vector of latent categories that are present in each entry, and a set of vectors of substrings that are in a given latent categories. So this vector describes what is our latent category. Here is a representation of what we have. I've run the model with dimension 8, and I've shown you the encodings that it gets. So each value is a continuous value that loads on one or more of the 8 dimensions. And so you can see that those are quite sparse. And here, for instance, we've identified managers. Here, we've identified operators. We can even infer plausible feature name simply by looking at the words that are often loaded on these. For instance, here we have manager, program. Here we have rescue. So we have an encoding, which is a numerical encoding that has been fully inferred from the data and that has meaningful names and meaningful categories. Now, if we want to do data science, often we want to communicate insights from the machine learning model. And for this, we might think that we need to curate the data. No, we can use feature importances. So given a fitted model, figure out all of the different features, what importance they have in the prediction, and we can use this on the representation that I've shown you before. And so now if we can look at what's important to predict the salary, well, apparently the most important aspect of the data to predict the salary is to be a manager or in management or in property. This makes sense, this is meaningful, and I did not have to clean the data to do this. Now, one last thing, our data may have missing values. And we want to do machine learning with this. So why doesn't the bloody machine learning toolkit work? Well, the underlying problem is that the machine learning models need entries in a vector space or at least a metric space. So it's a bit more than an implementation problem. A small note, categorical values are discrete anyhow. So if you have a categorical variable, a clean categorical variable, the solution is simply to create a special category, which you call missing, and to encode the missing values in this category. The rest of the talk, I'll focus on missing values in numerical variables. So there's a classic statistical literature on this, and the underlying model is that we have first a complete data generating process. Second, a random process that occludes the entries. And for a specific missing value situation, missing at random, which is defined as the probability of missingness does not depend on the non-observed value. Then there's a very powerful theoretical result that tells us that in this situation, in the missing at random situation, we can still do maximum likelihood while ignoring the unobserved value and retrieve a good maximum likelihood estimate. So there are other variants of missing values. One, which is a subtype of missing at random, which is missing completely at random. Missingness is independent from the data. It's easy, the results above still hold. And another one, which is missing not at random, which is we're not under the assumptions of missing at random, and in such a situation, the missingness is not ignorable. So it's a challenging statistical problem. Here are a few observations. I'm showing the complete data, the missing completely at random. You've seen that we have only, randomly losing data points, but there's no structure in this. And the missing not at random. And we see here that we have censoring basically above certain threshold, we're starting to lose information. And we can see why this distorts the data. Now, there's a big theory here of statistics, but first, there isn't always an observed value. What's the age of the spas of a signal? And second, we're not trying to maximize likelihoods, we're trying to do machine learning and prediction. So this theory doesn't completely apply to machine learning. Yet, the bloody machine learning toolkit still doesn't work. What can we do about this? The first thing we can do is imputation. We can replace the missing values by likely values that they may take. So there's a large statistical literature here, but they're really focused on in-sample settings. What about machine learning? How about completing the test set with the train set? What to do with the prediction target Y? So in scikit-learn, we have a few imputation procedures that will work out of sample. The mean imputation, which is a special case of univariate imputation, so replacing the missing value by the mean of the feature, this can be done by the simple imputer. From the classical statistical point of view, this is really a bad idea because it distorts the distribution. You can see it here. We've replaced on one feature missing value by the mean of the feature, and it creates a line that you can see with your naked eye in the distribution. And standard statistical point of view of missing value tells us that good imputation must preserve data properties used by the later analysis step. So for this we can do richer imputation. Conditional imputation, for instance, where we model one feature as a function of others. The problem is that it's costly, especially on large databases. It scales extremely poorly. One possible implementation is to iteratively predict one feature as a function of others, like in the famous mice software, and in scikit-learn this is done by the iterative imputer. So, we did a bit of theory. We looked at this problem from a theoretical standpoint, And so in the paper by Julie Josse et al., and our recommendations are that we found that they're basically different regimes. In statistics, typically you prefer the conditional imputation because it's richer. However, in machine learning, we showed that mean imputation is typically sufficient if you use a powerful nonlinear learner, because the nonlinear learner will basically detect the irregularities like the line that I showed you before and will predict very well from these. Now there's another approach that works only with trees, but trees are very good to deal with data that has a discrete or semi-discrete topology. And so you can adapt the trees to work directly with the missing values. So you can learn trees that make their decision on whether the feature takes certain values, including missing value. And so it readily learns to handle missing values. This in scikit-learn is exposed in the hist gradient boosting classifier and the regressor. And so what we see empirically is that this approach, the handling missing values inside trees, works extremely well, and that if you have enough data, mean imputation also works well. Now, imputation may not be enough. For instance, consider the pathological case where y depends only on whether the data is missing or not. For instance, in tax fraud detection. If you impute perfectly this data, you break the prediction. It makes the prediction impossible. The solution is to add a missingness indicator. So if you take an imputer, you use adding indicator equals true. Now, if we go back to simulations, what we see is that if we're imputing, this indicator is necessary for the iterative imputer, but it's not for the mean imputer. And using the support of missing values inside the trees works very well and does not need this extra indicator. So the take-home message is that practically using the native support of missing values in trees works best. And if we do imputation, when we have missing not at random situations, we really need to add an indicator. And in this situation, iterative imputation can be detrimental compared to mean imputation. So, to summarize, how do we learn on dirty tables without cleaning? We will prepare the data with a column transformer, and quite often, it's best to use the hist gradient boosting classifier or regressor. This is a good default as a learner. If we have dirty categories, we can do statistical modeling of the non-curated categorical data by capturing its string forms. And so we can use similarity encoding or other string-based dirty category encoders that can be found in the Dirty Cat software. If we have missing values, the best option is to use the native support in hist gradient boosting regressor or classifier. If we cannot do this quite often, it is enough to use the mean imputation and possibly to add a missing value indicator. This is ongoing research, and you can find more on the Dirty Data project. Thank you.